Hello, everyone, and welcome to our first official lecture. We're going to be covering Chapter 1, The Chemical World. This is a pretty simple and quick chapter. We're going to move through it quickly as a result. There's not too much going on in this chapter. It's here just to kind of introduce you to chemistry, get you thinking about, science, these type of things. We'll cover a couple things that will be important, but ultimately not much of this chapter is going to be represented on the exams and the final. Just a little note, I'm not going to read every single word off the slides. There's no point in that. You can pause the video, read through them, take any notes, but really I want you to, take the lecture notes and what I have to say in combination and use that for your, studying. So first, I'm going to always provide key concepts. These are what I'm going to focus on. This is what you should study on. So for chapter 1, what is chemistry? That's kind of what we're going to get into. The book has their definition. I have my definition. They're about the same, just focusing on minor different things. I like to think of chemistry about as how electrons move between different atoms and molecules, where the book just kind of states it as how things interact between different atoms and molecules. What is matter? Matter is anything that's made up of different chemicals, something that you can interact with physically. So that leaves what is not matter. Matter is things that you cannot interact with physically. So electromagnetic waves are going to be the number one source of non-matter things in the universe. Light, heat, magnetism, those type of things. Um, the scientific method is kind of how we approach science. It's a formulated pathway, where we kind of look at something, we make a guess about what's going on with that, and then we try to figure out if our guess is correct or not. And so these are the four things that we're going to be really concerned about with this chapter. So the definition of chemistry, the book gives you how matter behaves and what atoms and molecules do. I like to think of the electrons because in our sense of chemistry, the electrons are really what's doing everything, but that's not super important at this point in time. So atoms. Atoms are the building blocks of everything that we see and interact with around us. We can break these atoms down to, subatomic particles and fundamental particles. We'll talk about the subatomic particles, but we're not going to break down the subatomic particles and their fundamental particles. That would be a particle physics class. This is just an intro to chemistry class. We're going to keep it nice, simple, start out very slow and work our way up in complexity. Right now, we're just going to introduce the atom, which is our building block as chemists. There are other building blocks that you can work from, but as chemists, we work with the atom. So atoms, if they're combined together, give you a molecule. So here I have a water molecule, one of the most important and well-known molecules in the universe. Water is composed of these two hydrogen molecules that are on either side of a central oxygen molecule, and they have this bent-like shape that's about 130 degrees. The orientation and the specific atoms are what determine all of the properties of the molecule or the chemical. So the book gives the example of if water was linear instead of this bent shape, this kind of V or upside down U, however you want to think of it. If it was straight, just 100% linear, 180 degree angle instead of this 130 degree angle, water would be a gas at room temperature. And seeing as our bodies are mostly water, human life and all life as we know it would not be possible. Everything that we know as a cornerstone of nature would not be the same just because of the degree of angle between the two hydrogen atoms and the oxygen atom. So that hopefully kind of elicits the importance of shape and order. If I switched this hydrogen for this oxygen and I had oxygen, hydrogen, hydrogen, that'd be a very, very different chemical. Same way as if we changed the geometry of the molecule. So chemicals are everything and everywhere around you. You have a computer in front of you. You probably have a drink or a seat or furniture around you. These are all made of chemicals. Anything that you can interact with, touch, manipulate, taste, smell, feel, these are all chemicals. Feel, I guess, is a little bit of a stretch because you can feel electromagnetic waves. That's not a matter. So you can feel heat. But heat, light, magnetism, sound, these are all things that are not chemicals. So typically with chemicals, we get the social media picture of people, dumping toxic chemicals into streams, into the wildlife, or, paint thinners or other industrial chemicals used for, abrading concrete or etching, things like that. However, that's not always the case. There absolutely are those chemicals, but most chemicals are the air we breathe, the food we ingest, the things that we drink, the toiletries we use in our, beauty routines or our daily, getting around the house routines. So chemicals are everywhere. And chemistry tries to explain what's going on with these chemicals and be able to even make predictions about chemicals that we may have not seen. These are how pharmaceuticals or new engineering materials are devised, as people look at chemistry that's already existing and they understand certain phenomenon or patterns. And then they say, okay, I think if I do this, I'll have these type of properties, or even better of this, that, or the other. And so as chemists, we try to understand, explain, and then predict things. Science isn't really useful unless it can make predictions. And so the end goal of science is always to make a prediction. Now, oftentimes those predictions are wrong, and we have to refine our theories. The way we do this is through the scientific method. Now, the scientific method has changed and can be compressed and, compressed and extended, and depending on how complicated what you're trying to evaluate is, it can be very simple from, if I drop this apple, it's going to fall to the ground. That's a hypothesis. I would test that by dropping the apple. And this is a transfer from just kind of understanding through feelings, in the early, centuries, 1,000 years to 1,500 years ago, we thought we were the center of the universe because we always observed that we moved around things. Things moved around us. Not that we moved around other things. But it wasn't until we took a scientific method and a empirical approach that we were able to determine that, we're not the center of the universe. Just because something feels or looks a certain way doesn't mean that it is a certain way. So the scientific method can largely be broken up into a couple things. You have observations, hypotheses, experiments. Experiments, hypotheses, and observations will lead to strong theories and even laws. So a law is the most concrete thing. We have the law of gravitation, the law of constant composition, the law of conservation of energy and matter. These are things that we have never, ever observed to be incorrect. No matter where you look at them, any place in the universe, they always are proven true. Theories are sometimes laws that haven't been fully, extrapolated or fully, experimented on to get to that concrete level of a law. But a theory is a well explained and well observed phenomenon that is true for nearly all cases that we can come up with, and we just aren't really confident yet. Or maybe there's a tiny little asterisk next to it that, under vacuum or at 1,000,000,000 degrees Celsius, these things kind of fall apart. So you have things like the theory of relativity, which for all practical circumstances is 100% true. But if you take it to the extremes of the physical world, absolute zero, the highest temperature possible, which I don't know what the number is for that. It's based on wavelength calculations. Those type of things, the theory of relativity falls apart. As you get close to the speed of light, things start to get weird. And so we would call that a theory rather than a law. Very minor difference, not going to be a big deal for this class. So, observations. You can't do any science without making observations. We have to look at things. We have to observe. If we don't observe, if we just have our blinders on and we don't listen to anything, we don't smell, we don't taste anything, we're not interacting with anything and we can't pose any questions. So you always want to have a careful eye and be curious about things. Next is we have a hypothesis. After we've made an observation of something, I saw a leaf falls to the ground and I say, why do things fall to the ground? And I could make a hypothesis as, oh, well, there's some sort of force that pulls everything into the Earth's center at a constant velocity. Well, I could test that. I could, drop things from different heights and then measure the time that it takes to fall. If the average speed is the same for every single one of them, that means that things travel at an average velocity when they fall. However, this is falsifiable because if I drop that and I measure from different heights, I'll notice that these things, the higher I drop them, the higher their average speed is. So that would indicate that, oh, they don't have constant speed when I drop them. They have constant acceleration. And then I could go test that and further, and eventually I would come up with the universal law of gravitation, which is a law that through multiple falsifiable experiments becomes a essential fact. We can treat laws as facts. We don't like to say things are factual in science because there's always wiggle room for things to change or for us to understand things better. But laws are kind of that exception of we've fully vetted this and we believe that we understand this to the nth level. So hypotheses are ideas, are educated guesses. And in order to, act upon these hypotheses, we have to have some sort of experiment. So the experiment is basically us just testing our hypothesis. If I think that things will fall to the earth at a constant velocity, I have to measure their velocities as they fall. There's a whole bunch of different ways to do this. I can do it by averages. I can do it instantaneously. I can do it in piecewise. Certain things have better statistical relevance, and that's why we have to really think about well-developed experiments. In general, we can treat the scientific method as this kind of diagram here, where we have some sort of starting point, which is essentially the observation. We view something. Something happens. I watch a leaf fall from a tree to the ground. We then form a hypothesis. Oh, all the leaves essentially hit the ground at the same time, so things must fall at the same velocity. We would test that through an experiment. I would drop things at different heights, see, what happens, and maybe I do that with leaves, and I notice, oh, they do all travel at the same velocity. Let's try it with different objects. Now I try it with rocks, and it breaks my hypothesis. And it's like, that doesn't make sense. So now I need to reevaluate it. And then maybe I might come up with the idea of, oh, there's air resistance or drag. And so now I have to incorporate this into the hypothesis. And we test, and eventually that becomes the law of gravitation. The whole idea is that we make an observation, we make a guess on what's going on or a hypothesis based on that observation, and then we test it. And we revise our hypothesis, our theory, or confirm the law. So the scientific method has done wonders for us. 200 years ago, we thought everything was just magic. Spontaneous generation was how we thought that flies occurred. We had no idea that they came from maggots and then metamorphosized into flies. The same thing with atomic theory. 200 years ago, we were just mixing chemicals, making dyes, hoping things worked and didn't kill people. Now, we have, through the scientific method and rigorous analysis and experimentation, we've advanced technology so far that we can image single cobalt atoms on a copper screen. And so someone actually took an AMF device. It's basically can modulate things by the frequency of the atom and position them in essentially a perfect circle with, these outlying dots. We can actually visualize these fundamental atoms, which is something we couldn't do. And it's only because of the scientific method that we've been able to, expand and develop. So here's a couple questions. I'm not going to give you questions like these, but essentially all of these are based on the law of conservation of mass. So when a metal is burned in a closed container, the mass of the container and its contents do not change. This is just a statement. A law is a statement. It's just, if this, then that. It just is what it is. So we would say A is a law. Matter is made of atoms. This is an observation, a theory. You could call it a law, but it's something that's always observed to be true. And this is where it kind of gets, taking just a single statement can kind of be finicky about whether it's a law, an observation, or a theory, because a law is based on a theory, which is based on an observation. So there's a little bit of overlap in all of these. Matter is conserved in chemical reactions. This is the conservation of matter, which is just a different variation of the conservation of energy. Energy and matter are correlated through Albert Einstein's equation, E equals mc squared. Energy equals mass times the square of the speed of light. When wood is burned in a closed container, its mass does not change. So this is more of an observation, where this is the statement of the law. Really, both of them are explaining the same thing, and that's why I'm not trying to trick you on anything. You should be aware of theories, laws, but I'm not going to split hairs on, giving you a statement and making you evaluate whether it's X, Y, or Z. So, as chemists and scientists, it's very important that we can analyze data. And so we'll be given tables like this, and you'll have to do a whole bunch of things with this. For this table, what they're trying to exemplify is the law of constant composition. So if you notice, and the conservation of mass, law of conservation of mass. So we have 20-gram water sample. That can be broken up into 2.2 grams of hydrogen and 7.8 grams or 17.8 grams of oxygen. If we add those two numbers together, we get exactly 20 grams. So that's the conservation of mass, the law of conservation of mass. And then we have the law of constant composition, which basically says that all all compounds or molecules have the same composition. Every water molecule is identical to every other water molecule. So the relative ratio of hydrogen to oxygen will always be the same. We showed earlier there's one oxygen to two hydrogens. That's always going to be the case. So if we were to take the ratios of 2.2 and 17.8, 5.6 and 44.4, 11.1 and 88.9, we divided all those numbers by their partners, we would get the exact same ratio or fraction or decimal. And that's because all of these things have the same format, the same formula. It's just, in one case we have 20 grams, 50 grams, or 100 grams. That's all that's different. And we should be able to look at these charts and pull out all the necessary information. This is a tabulated chart. We see these quite a bit. We kind of went over the patterns. But we also have graphs. Graphs are probably the more useful type of interpret or data that you would interpret, just because it's quick. Over here, I can look and say, I can answer all of these questions really quick. It took me, 30 seconds to a minute to explain all of the data in the tabulated data, because I have to look through every piece and piece it together, compare A to B to C to D. And here, with a graph, I can just go, okay, concentration of CO2 at 1970. I'll just go to 1970, and then I go to where the trend line is. Oh, right here. So it's about somewhere between 330 and 320. So we'll say 325 just for ease of measurement. And then we do, 2020. We just go to the end because that's where it capped out. And we say it's about halfway again. It's not quite halfway, but we'll say it's halfway for ease of conversation. So we'll say it was, 415. Then we'd see how much did the concentration increase. We'd just subtract those two numbers. So if we forgot, this one was 325 minus this one was 415. We'd plug that into our calculator and get the answer. Really quick, easy. You just want to find the intersection of what you're concerned with. So we're concerned with carbon dioxide concentration, and we're given 1970. So we go to 1970, and we just find where we have an intersection with our graphed line. And then we track where we are on the y or x-axis, depending on which one we started at. So, couple tips for, being successful. There's no one way to be successful in chemistry. You don't have to follow these rules. They're just helpful tips. And these are generally amendable to all science, not just chemistry, but STEM in general. You don't need to be. The more curious you are and the more creative, the more thoughts you have about the world around you, the more you're going to learn. as a scientist because you're just going to be interested. You're going to be asking silly, weird, nonsensical questions. And even though some people get annoyed with that, that's how you learn more than anything. I learned more in my first, 6 months of working in a lab because I just asked every little thing that came to mind. I was curious. I wanted to know, why did this thing catch fire but this thing didn't? Why did this shine a pretty color and this one is just white all the time? All these nonsensical questions really lead to a wealth of knowledge, and you shouldn't be afraid to ask any question that you're curious about. One thing you do have to do, and there's no way around it, is you have to be able to do calculations. You have to be, math literate. You need to be able to do, conversions from grams to moles to kilograms to Celsius to Fahrenheit. All these things are going to be essential, not just for chemistry, but science as a whole. Biology, you can get away with a little bit of not being the best at math, but the harder sciences like chemistry, physics, mathematics, engineering, you're going to really need to sharpen your math chops if it's been a little while. And we have reviews for that. If you, need anything additional to what's already available to you, just reach out to me. I'm happy to source something or just give you extra resources that I've accumulated over the years. So chemistry requires commitment, and it doesn't matter what that commitment is. You can get by with just coming to class and going through the motions. Absolutely, you can get by, and maybe you'll get better than a C. That would be awesome. But you need to be consistent with putting in the work, whether that's homework, whether that's study groups, whether it's watching, YouTube videos every night on the topics that don't make sense to you. All of those are great. Me personally, I never did homework ever in my undergrad. Minus the couple times where it was absolutely required, but I often just didn't do it because I didn't care. What I did was I spent 30 to 40 hours a week in an actual research lab, working hands-on with chemicals, learning practically. And so that was my practice. That was my regular commitment. 30 to 40 hours a week was, more time than I was spending in the classroom. And so I got a lot of practice and never needed to do the back of the book homework problems like many of my other students did, or many of my other peers needed to have the same level of success. However, you can get a benefit out of studying your chemistry, whether that's practical, whether it's hands-on doing the problems, or if it's teaching someone how to do stuff. All viable methods of practicing and committing to chemistry. You just need to have some sort of regular interaction with chemistry to really succeed, because it's an awkward, weird thing. So real quick about the text, the back of the book problems, as I call them, all of the odd answers are answered in the appendices. They can be a little hard to find in the e-text, so if you're confused about it, we'll go over this in lab so we can actually nitty-gritty get into all the different chapters. So just to remind you guys, not much is going to be represented in this chapter on the exams. It's just kind of to get you thinking about things, introduce you to the world of chemistry. Again, what is chemistry? It's the study of how things interact with each other. Specifically, we want to look at how atoms and molecules interact with each other. They interact through their electrons, so I like to look at it from an electronics perspective, but that's not necessary. What is matter? Matter is anything that's made up of chemicals. What does not matter? If matter is everything that's made up of chemicals, everything that's not made up of chemicals is not matter. So electromagnetic waves, light, heat, magnetism, electrical potentials, all of these things come from chemical. Well, I shouldn't say all of them, but 99.99% of them all come from chemicals, but they're not chemicals or matter themselves. Then we have the scientific method, which is essentially making observations, hypothesizing what's going on with these observations, making experiments to test our hypothesis, to either refine or to refute our hypotheses so that we can make theories and laws about the natural world. That's going to be chapter 1. I will talk to you guys next time on chapter 2 and see you guys in lab this week.